If we take a look at this reaction of ammonia inside water as the solvent, then we will produce OH minus and NH4 plus. In this case, we should write down H2O because we need a source of oxygen for the OH minus. And now if we again try to complete our ice table and say again, just for the ease of calculations, we have 0.1 molar of NH3 in the beginning. In this case, we do not have OH minus and NH4 plus. Therefore, at the change part, we can write down that we have here minus X, this one plus X, and this one plus X. Now, in this case, we need to write down the phase because H2O is liquid. Therefore, we do not include it in our mathematical expression for the equilibrium constant. So, at the equilibrium, we will then have 0.1 minus X. This one is minus X. This one is plus X and plus X. And similarly, just like what we did for the acid, in this case, we use Kb because it's a base instead of Ka. And it's going to be equal to X multiplied by X divided by 0.1 minus X. Again, we do not include this one, the water. This one is not included. Oops. Okay, so I will just write it down, not included, because it is a liquid. Again, the assumption is that the Kb is smaller than 5% of the initial concentration of the base. Let's write it down as BOH. So this one is a base. For instance, this is BOH. Initial concentration, in this case, is 0.1. And the Kb, if it is 5% smaller than Kb, then we can also assume that X is super small. So we can then transform this equation into this form. Kb is equal to X squared divided by 0.1 only. So now X will be equal to, again, square root of Kb multiplied by 0.1. However, here be very careful. The X, in this case, is actually over here, which is the concentration of OH minus. So in this case, what we can immediately calculate is first the POH. So POH is minus log of OH minus, therefore it is minus log X. And after we obtain the POH, we can obtain the pH by taking the number of 14 minus POH, because POH plus pH is 14. So this is how we calculate the pH for weak base reaction. Now we will discuss about how to determine the pH of salt solutions. Now, from this we can classify 4 situations. The first one is when we have a salt that comes from a strong acid and a strong base. For instance, NaCl, which comes from or originates from the reaction of HCl, which is a strong acid, and NaOH, which is a strong base. Now, for cases like this, the pH of solution is always 7 because it comes from a strong acid and a strong base. Next up, we have the sodium acetate, or NaCH3COO, and this is actually a salt that comes from a weak acid and a strong base. So CH3COOH, or acetic acid, is a weak acid, and NaOH again is a strong base. Together they will form this salt, and these types of salt will have a pH that is higher than 7. We will see how we can calculate them in a bit. Third one would be salts like this, NH4Cl, or ammonium chloride. And this is a salt that comes from a reaction between strong acid like HCl and weak base like ammonia or NH3. And in this case, the pH of such solutions will be lower than 7. So this will be a base salt or basic salt, and this will be an acid salt or acidic salt. And finally, we can have a weak acid and weak base combination. For instance, the ammonium acetate, NH4CH3COO, or if we condense this, it will become C2H7O2N. This comes from acetic acid plus ammonia. So the acid is weak, the base is also weak. And in this case, we cannot determine the pH easily because we have to take a look at the Ka of CH3COOH and the Kb of NH3. The one that is bigger will determine whether it is going to be an acid or it's going to be a base, and whether the pH is going to be lower than 7 or higher than 7, or in the case where the Ka is exactly the same with the Kb, and then we will get a system that is also neutral. So the pH will also be 7. Okay, let's take a look at this basic salt, CH3COONA. So in water, this salt will first dissociate into its cation and its anion. Now, Na plus is a neutral salt, so this will not play any role in determining the pH. Its conjugate, quote-unquote, is NaOH, and because NaOH is very strong, then Na plus will be weak. On the other hand, CH3COO- is a conjugate of CH3COOH. And since CH3COOH is a weak one, so weak acid, its conjugate will be the inverse of it. It will be a quite strong or considerably strong base. So the one that will cause the basic properties here is actually the CH3COO-. Therefore, now we have to write down the equilibrium that shows the basic reaction based on CH3COO-. So CH3COO-, we have to add H2O liquid so that we can have a source of OH-. And then, because H2O will lose one of its protons, the proton will be accepted by CH3COO-, so now it will become CH3COOH. So now when we have this, it's the same old ice table. So again, ice table, and then depending on what you have in the beginning, say again, just for the sake of calculation, we have 0.1 again, molar. Then this will be like this, plus X, those side minus X for the reactant, plus X for the product. At the equilibrium, we will have this number, plus X and plus X. Then we can build again the K. However, be very careful here. What is the K for this reaction? We have to be very careful here. What is the K of this reaction? You see that it's a basic reaction, so the K has to be Kb. How do we know that this is a basic reaction? This reaction produced OH-, so it has to be a basic reaction. So the K should be Kb. So the Kb will belong to CH3COO- because that is the base in the system. And we can calculate the Kb of CH3COO- by taking the Kw of water divided by the Ka of its conjugate, which is CH3COOH. So Ka of CH3COOH. And this is going to be equal with the equilibrium expression, which is again X divided by X, and then 0.1 minus X again. In the case where Kb is smaller than 5% of the initial concentration, so CH3COO- initial, we can also assume that X is very small. And then we can write down this following equation, where Kw over the Ka of CH3COOH is going to be equal to X squared divided by 0.1. Now X is gone because it is super small. So then again, now we get the X, which is square root of Kw divided by Ka of CH3COOH multiplied by 0.1, which is the initial concentration. Now X, we will take a look at our table and see that X is OH-. So again, what we can calculate from here is the POH, which is minus log OH-. So it's going to be minus log X, and the pH is going to be equal to 14 minus POH. And since it is a basic salt, the pH will be higher than 7. But how much higher? We can calculate it from this methods of calculation. Now, similarly, What if we have an acidic salt? NH4Cl will first dissociate into NH4 plus and Cl minus. And Cl is a neutral species because Cl minus is a conjugate of HCl. HCl is super strong, so Cl minus is really, really weak. So it will not influence the pH of the solution. On the other hand, NH4 plus is a conjugate of NH3. NH3 is a weak base, therefore NH4 plus is a considerably strong acid. Therefore, the acidic properties over here actually comes from the NH4 plus. So let's write down the acidic reaction now. So again, we have NH4 plus. In this case, if it's an acid, you can write it down immediately like this, so releasing H plus. Or if you want to write down water, it's okay as well. So NH4 plus water, H2O. You will have to write down NH3, but here you have to write down H3O plus. H3O plus is the same with H plus. Okay. So now again, we will have to build the ice table. So ice table again over here. And now just assume one more time that this is 0.1. This one is not existent in the beginning. This one as well. So this one is going to be minus x. This one is plus x, although this is liquid, so will not influence in any way. This one is minus x. Yeah, because it's a reactant. And H3 will be plus x. H3O plus will also be plus x. So at the equilibrium, we will have this concentration, that concentration, and that concentration. Now, let's determine the K. In this case, the K will be a Ka. How do we know it's an acidic reaction? Because it releases H plus. And we can also calculate Ka of NH4 plus by taking the Kw, which is 10 power to the minus 14th, divided by the Kb of its conjugate, so NH3. So now let's build our mathematical expression. Kw over Kb of NH3 will be equal to, again, x divided by 0.1 minus x. Again, if the x is small, as usual, we can assume that it is negligible. So Kw over Kb will be equal to x squared divided by 0.1 only. X is going to be equal to the square root of Kw divided by Kb of NH3 multiplied by the initial concentration of the NH4 plus. And in this case, we can see that X is H3O plus or H plus. So we can immediately calculate the pH. pH is minus log H plus or H3O plus, that's the same thing. pH is minus log X. And don't forget, in this system, the pH is going to be smaller than 7 because it's an acidic salt.